Hello, we will start the meeting very soon. Before we start the meeting, could anybody take care of Java? It's very simple, so could anybody volunteer? Someone who can take care of Java, please raise your hand. Oh, Miria, thank you. Okay. Okay, let me try. Take it off. Take it away. Like this. Like this. Okay. Okay, let's get started. Hello. So welcome. This is TCPM working group meeting. Just you make sure you are in the right room. Okay, my name is Yoshifumi Nishida, one of the co-chair of TCPM working group. And this is also Michael Sharp, and a co-chair of TCPM working group. And unfortunately, Michael Jackson cannot come to this meeting, but we expect he will come next meeting. Okay, this is user not well. I think you already familiar with it. Basically, what you say in this meeting will be governed by this not well. And if you want to take a look carefully, please go to the IETF webpage, or you can Google it and then you can find the not well very easily. And note taking, I appreciate Gori to take note taking, and Maria, thanks for Java. And before we start the meeting, one thing we would like to remind is when you speak up at the microphone, please say your name beforehand so that note taker can track your name. Also, when you submit your internet draft, please include TCPM in your draft name so that chairs can track the status of your draft. Okay, moving on. So this is the agenda of today's meeting. At first, chairs will talk about working group status. And after this, we have 4 presentations for working group items. First, Naeem will talk about alternative backup draft. After this, Marcel and Bob will talk about generalized ECN. And after this, Bob and Miria will talk about accurate ECN draft. And after this, Yuchun will talk about TCP wrap. And after this, we have 2 presentations for individual document. Marcelo and Yoshi will talk about the ESN draft, extended sequence number draft. And after this, Praveen will talk about update on Windows TCP. Any questions or comment on this agenda? Okay, moving on. Status of document. And so recently, DCCP draft has been published as RFC 8257. Congratulations, and I appreciate your cooperation. And then for cubic draft, we got approved from IESG yesterday, so we will soon, this draft has been published. Okay, and we appreciate your cooperation to proceed this draft. And then we have several active working group documents. So first one is alternative backup ECN draft. And this is one of today's agenda. And in the last meeting, we got several reviewers, volunteer reviewers for this draft, and then we started receiving the reviews from the reviewers, and which is pretty nice. So I think this draft is getting very matured, and so after we receive another one review or something, and then they can revise the draft, and then if everything goes smoothly, I think we can proceed to the working group last fall. So our expectation is, within a month or so, we might be able to proceed to working group last fall. That is our expectation. And the next one is accurate ECN draft. This is also one of the agenda of the today. And this draft has been updated very recently. So I think, let's discuss in the meeting. And generalized ECN, this is also one of the agenda of the today. And this also has been updated 2 weeks ago or something. So let's discuss the update in this meeting. And LAC draft. This draft has been quiet for a while, but they also seems to have some updates on this draft. And then this is also agenda of the today. So let's discuss in the meeting. And EDO draft. I think this draft has been quiet for a while, but according to the authors, authors has some plan to do some experiment, and so we expect the author will come back with new version of the draft with some result. About RTO consider, I think this draft is getting very matured, but in order to finalize this draft, we have to sort out some points. And the main point of the discussion is to keep consistency with the related docs, because RTO consider has some related docs, such as RFC 8085 or RFC 6298 or RFC 793 or 793 bis. So we have to make sure each draft do not contradict each other. So we try to make some, chairs have some discussion on this draft, and then try to make some proposal to the authors of the text that do not cause any conflict with our document. That's our, right thinking right now. So, and then if that doesn't work well, I think we might think about other plans. But right now we are trying to focus on make some proposal to the authors, so which can also agree. That's the plan for the chairs. And then about the 2040 base draft, in the last meeting, we did a working group adoption call, and then as a result, this draft has been adopted. And so right now we are trying to prepare the milestone of this draft, but there are some discussion between the author and then chairs. And then the chairs made several proposals, and then I think they also agreed one of our proposals. So our expectation is the author will update draft based on our suggestion. That's the current status. Any questions so far? Okay, moving on. And then 793 base draft, unfortunately, Wes cannot come to this meeting, but we got some text from him, so I will talk about it on behalf of the author. So as you might notice, 03 version has been submitted about 4 days ago, and there are several open discussion items in this draft. So Wes start opening the thread on the mailing list with the following titles. So the thread will, he will try to open 4 threads, I think. And then after, we settle down all open discussion items, new version will be submitted in December, closing all the item marked to do in the draft. That's the plan. Okay, any questions so far? Okay, moving on. And then finally, I would like to talk about MPTCP converter draft. And so right now, chairs are having a plan to run adoption call on MPTCP converter draft. So to be clear, we are going to run adoption call. And then when we run adoption call on this draft, and if it's accepted, well supported, MPTCP converter draft will be a working group item of TCPM working group. That's the plan. So let me briefly describe the background of this draft. So this draft name is Draft Punabetra MPTCP Converter. This draft has been presented in the last MPTCP meeting. And then this draft is mainly designed to assist the deployment of multipath TCP. But if you look at this draft carefully, if you look at the architecture in the draft, this draft has a certain generic architecture. So to be clear, I don't say very generic, or I don't say less generic, because this will be a part of your decision. So it has some generic mechanism. So, and if the architecture in this draft is generic enough, we can apply this technology to other TCP extensions, such as TCP Inc. might be very useful. We can apply the same technology to this thing. That's maybe very interesting use case. So if this draft can have a generic mechanism, it will very make sense to have this draft in TCPM working group. And so if you are interested, please see Olivier's email, which he sent very recently, several days ago. It contains lots of useful information to understand that his draft, his intention. So please check. And then right now, we cannot discuss the technical detail of this draft, but we would like to hear some opinions on running adoption call in TCPM working group. So there are several options of the future direction of the draft. So chairs would like to understand what people think. So if you have some opinions, please speak up.
Mia Kulev, it's on, right? Yeah. Mia Kulev, as AD for both of the groups. So I would just like to repeat once again the request for reviewing this document. Even so, the use case is MPTCP, and that's a use case that makes most sense. I think what's needed here is like general TCP expertise, which is in this room. So please have a look.
Okay, thank you. Any other opinions? If there is no specific opinion in this room, we will run adoption call on the mailing list, and we try to get feedback from people.
David Black as TCP Inc. chair. Yeah, definitely double +1 the question mark there. I realize TCP Inc. is trivially man-in-the-middleable. However, publishing a draft that encourages that to be done in TCP Inc. is probably not a good move.
So what's your preference? What is your preference on this draft?
So David Black, so to be clear, I would not try to make this draft applicable to TCP Inc. I think that's basically, if you make this draft applicable to TCP Inc., you're describing a man-in-the-middle attack as a feature, I think, and that's not good. I prefer just have TCP Inc. probably left alone.
So it's not a man-in-the-middle attack. It's like if two or both of the endpoints would not support TCP Inc., there could be a middle box that would still support TCP Inc. and encrypt the traffic over the rest of the path. It's definitely not a man-in-the-middle.
And then TCP Inc. is not the only option. So there may be another TCP extension that we might be apply this one. Any other opinions? Okay. So, yeah, in order to get more feedback, we will run adoption call on the mailing list. Thank you so much. Okay, moving on to the working group item presentation. So first one is alternative backoff. 9.
The box.
So, okay, so let's try again. So this draft is basically an update to the alternative backoff with ECN. So next, please. In the last IETF, 3 persons were assigned to do the review. They volunteered to do the review. So we've got feedback from Roland. And then we've got also a couple of days ago, we got feedback from Lawrence, and thank you to them. Thanks to them. And we have incorporated these feedbacks that we received from them. So we have submitted 2 revisions over the course of the time between the last IETF and now. The revision 03 was submitted a while ago, and I just submitted the revision 04 last night. So what has been basically happening, we have tried to incorporate all of the comments from the 2 reviewers. Basically, we've got more consistent terminology and definitions. So there were things that were basically a bit more hand-wavy, and then we changed them and we make them to be more precise. And we define the stuff that were there, more precision in the language. We distinguish, for example, between what is a buffer and what is a queue, because both terms were used in the draft interchangeably. So we provided a more accurate wording there. Also, everywhere where we for example, mentioned loss, now we wrote as an inferred packet loss. So the language of the draft right now is more consistent with the RFC 5681 and RFC 3168 language, and the formula style that they have been using for setting the SS stretch and CWINT. Next, please. So we also provided some clarifications. One of these clarifications were on the safety of the mechanism. We explained that the worst case scenario basically with alternative backoff with ECN is no worse than the standard loss-based TCP, because anyways, let's say you basically don't react to ECN signals, you're still bound to the reduction based on the loss-based TCP's behavior as is described in the 3168 and in the previous RFC. And also there was some ambiguity about the scope of the document, because we somehow in the previous revisions provided some hints or recommendations that this could be used for other transports. Now we have a more clear language in the draft that says that this beta ECN that we are recommending normative language is only for the loss-based standard TCP. And also we removed the normative language for other transports, and now we only basically say that it's applicable for other transports that have a per RTT ECN response. So if there is a future draft, for example, on specifying SCTP's congestion control behavior, then it's up to that draft whether to adopt the alternative backoff with ECN with their specific beta value that they might want to use, or any other type of congestion control. So the scope of this draft is basically limited to standard TCP. The references are updated. There is no change to the technical content of the draft. Yes, please. Next.
It was Gori Fairhurst, and I was commenting as TSVWG chair rather than co-author. I think that's the right thing to do with things like SCTP and other transports. We can't make a normative requirement on future specs, but we can say that this is the right process. Whether we've got quite the right words, we can tweak them a little bit if we need to, but I think that's the right thing to do from TSVWG's point of view. Unfortunately, the ECN spec for SCTP was never adopted, largely due to a lack of progress with ECN at the time it was brought up. So that could become a future item, perhaps, if that happens. But at the moment, there's no reason to cite that old internet draft.
Sure. So I think we agree on that. So this is basically limited to what is in 3168. And so the references are updated. There's no change to the technical content. Next, please. And so we have, as we mentioned previously in Prague, we have submitted a patch to the FreeBSD upstream. Over the course of this time, this patch was being reviewed. Now the review is complete. We expect that it appears on the FreeBSD's mainline kernel quite soon, in the matter of days, if not hours. And we've got also a patch for Linux, which has been there for a while. So this is kind of becoming available in OSs eminently. Okay. And I think that's all.
Any questions?
I have a question on the implementation. So the draft says the value should be recommended value is 0.8, right?
What is the recommended values?
Yeah.
So we recommend for the standard TCP, we recommend to use beta 0.8.
0.8. So my question is,
For
are these
ECN.
implementations using 0.8?
Sorry?
Are these implementations using?
Yes, by default.
Has there been any experimentation done to see if after applying the value of 0.8, is there a loss in the subsequent RTT?
Sorry, can you speak a bit louder? I think the mic is not working as it should.
Working.
Okay.
Give it a minute. It has to go green. Now try it now.
Hello.
There
Yeah.
you go.
Yes.
After applying the reduction factor, has there been any experimentation done to see if there is a loss triggered in the next RTT, and would it make sense to make the backoff more aggressive for subsequent?
By backoff more aggressive, you mean to reduce
Yeah.
more?
Yeah.
So we haven't been looking at the loss behavior, but of course the AQM mechanisms, they have got a protection mechanism. So if you have an unresponsive traffic, so you anyways would be.
I guess my
dropping
question
packets.
is, you don't know whether there is AQM. So if you make this change, I need some clarification here.
Sure. Okay, but the fundamental basis for the A work, and this is Gori Fairhurst as an individual author this time, was that if you see loss ever, you use the standard TCP values for beta. The change is only when you see an ECN mark. If you ever see loss, you behave as a normal standard TCP would behave.
I think but my question is, even if you get an ECN mark, so this is deviating from what the original RFC said. There is a potential that you might get more ECN marks or even a packet loss in the very next RTT. So my question is, should we be more conservative in such a case?
What happens if you get ECN marks and loss in the same round trip time?
You take loss. You do the loss reaction and the reduction that you would do for loss.
Because usually you only reduce once per round trip time, right? If you get the ECN marking first, you reduce by 0.8 and then you get a loss later on and you would reduce further?
Yes, so
That's implemented.
well, I can't say it for sure, but
That's kind of a little bit your question.
Have,
Yeah. Okay. So
yeah.
check, make sure, and maybe
Yeah.
clarify in the draft as well. I don't
Sure,
know.
I can clarify that.
So you're saying is the reduction by half of what you did after ECN, or a half of the original? Right, is it half of 0.8 or
So
half?
the only
of what?
change that we make is that whenever in the previous, like everything else is the same in RFCs. The only thing is that whenever you receive an ECN mark, basically you go by 0.8. So if normally you would react once per RTT, So if that's the case, we didn't touch anything else. So then it should happen that you would go down by 0.8. But then of course you may subsequently receive a packet loss in the next RTT. So, but I can definitely check against the patch and see. This is not something that is explicitly in the patch, so I can see what happens to this behavior.
David Black, let me sharpen Miria's point because you came very close to it. What you just described was ECN mark in one RTT, loss in next RTT. What I understood Miria to be concerned about, and I share the concern, is you get an ECN mark in one RTT and you react, and then the stack says, and I'm not going to do anything again in this RTT, and while the stack is not doing anything again, a loss shows up.
Sure. Yeah, I understood that. I think,
okay. That's
something
that you did. Yeah. That's something to be careful about, to have ECN marking masking actual losses.
Sure.
Do you want to speak on that?
Michael Wetzel. So this is not a comment, it's a question, because this isn't really about Abe, it's about ECN. I mean, in general, if you have an ECN mark and then you have a loss in the same round, I don't know what ECN does. I really
don't. When ECN is loss equivalent, i.e. before you do this, it doesn't matter because the reaction is the same. You did it once.
You do it once. Are you sure you do it only once? Does the standard say you do it
You're supposed to react once per RTT.
Okay.
Yep. I think we agree it's time to go and read the code for normal ECN and for Abe, because it's a separate bit of code, surprisingly. And let's just check.
Yep.
Abe does not change it. That's all I can guarantee. But the question is what happens, and I don't know what happens when you get the two bits of code interacting. Go on.
Marco, I suggest what you do, you read the ECN papers that Sally Floyd has written. She has been very carefully specified what to do.
Lawrence Stewart, as one of the people reviewing the FreeBSD code, and literally with my finger on the commit button as we were having this discussion, I've just held off for a second, but the code does hold, essentially it sets send recover in response to receiving ECN mark and does not apply any additional back off if a loss were to show up in the period, so we can alter that if we think that's appropriate. But as currently implemented, it would essentially do nothing until the send recover was reached, and then if a loss showed up after that, we'd have a 50% back off. But at the moment, it's only 80%.
Yep.
So, David Black, what I actually have to say is that I was third reviewer. I finally got the review done just in time, i.e. in the last 12 hours. It's on the list. It's almost entirely editorial. The only thing that might have a little bit of technical content to it is the draft has a very strong focus on recent modern AQMs like Pi and Coddle. However, this is obviously going to be deployed with whatever AQMs are out there, and a little more discussion of what else is or might be out there aside from dismissing red would be a good thing.
Sure.
Okay. Any other questions? Okay, thanks so much.
Okay.
The next will be ECN++. You want to start from this one? Yes. Yes.
Hi. Marcelo Bañuelo here, speaking for the authors of the ECN++ draft. Next slide. So in the last meeting, we basically have one open issue left. That is what to do with respect to PureAx. So there is a strong motivation for actually ECT marking PureAx because if we don't, when there are episodes of congestion, PureAx will be more likely to be dropped, which will result in performance impairments. So it would be useful to mark them to avoid this type of drops. The problem is, what do you do when you actually receive a CE? When the PURAC is actually marked with CE and you get an ECE back? How do you actually respond to that congestion signal? The issue that was noted in the previous meeting is that in the case that there is an endpoint that is only sending PURACs, and you actually respond to that congestion, you have a biased response, because the only thing you can actually have is response of PURACs having congestion, and eventually you reduce more the window, and you have no opportunity to increase the window. On the other hand, not responding to congestion, to a congestion signal that you actually receive, seems like the wrong thing to do. So the question is, okay. So the question is, how do we handle the situation, right? So after some discussion, the proposal that has been done in the mailing list is next slide, please. Is to only ECT marks PURACs in the case where ACCN has been enabled in the connection. The reason for this is because ACCN actually provides a more accurate information and reports the number of packets that have been CE marked, and also the number of bytes that encounter the congestion. Right, so that allows the congestion control algorithm in the sender to actually be able to respond to a much finer grain signal, because in the particular case of PURACs, the number of bytes that encounter congestion will be 0, right? Because the PURAC doesn't contain data, right? So this is basically the proposed way forward. We have mentioned this in the mailing list. There was no negative feedback. There was little positive feedback, but no negative feedback. So basically the question is if the working group feels happy with this, and we can close this issue this way. Comments?
Okay, Bob Briscoe as co-author. And we also need to make the point that the ACCN option isn't being stripped in order to do this response, because you need it to get the bytes. Okay. Because there's a case in, if a middle box is stripping it, you haven't got the information.
Right.
So this is Michael speaking from the floor as individual. So I wonder in general a little bit about the tight coupling between this draft and the accurate ECN1. So because some of these things in principle could be separable, but we now have two cases where we actually make a dependency on those two drafts. So I'm wondering whether that's really necessary, because from a high-level perspective, we look here at corner cases. I've been at one IETF meeting this week, in one IETF meeting, where there has been pretty fancy discussion on congestion control that is not only about ECN. And in those cases, I've seen pretty aggressive proposals. So I'm really wondering whether we need to deal with all corner ECN cases correctly. So to me, I think there could be ways how we could better decouple that draft here and the accurate EC1. There's a risk probably that some information gets lost, some marks maybe get lost. The question is, why do we really have to care about that if other transports are doing completely other things? And as I said, I think this draft could be simplified if we make clear how this could be deployed independent of accurate ECN and how it could be deployed with accurate ECN. But I personally would suggest to clearly define a mode where accurate ECN is not in use.
So, Michael, the draft, I think, currently contains that information, right? So the draft will basically say at this point that
but clearly separate one part of the section. This is how to use this without accurate ECN. Then another section, and this is how you do it with accurate ECN, and this is the added value. So clearly separate it.
This is essentially editorial, right? I mean,
Yes, it's editorial, but I mean, it could maybe simplify the document a bit and change things. It's mostly editorial, but as I said, I would look for clear guidance how to do this without accurate ECN. And as I said, for the Purac part, I'm still not fully convinced that you only enable it if you have accurate ECN. Maybe you can just do it without it.
Let's wait. There are too many things here. So the first thing is whether. Okay. So the current draft clearly defines what to do when ECN is negotiated and when it's not. Right? There is a table that actually describes which situations. This is perfectly described in the draft. I think it's. I mean, maybe there is some editorial effort that needs to be done to convey it more clearly. I'm happy with that. But the information is in there.
I agree. So,
okay.
So
whether the best approach is to actually have two documents back to back, one with accurate ECN or another, and another without accurate ECN, or to have the integrated version, that's an editorial discussion that we can have, and I'm happy to do that. Right. The first thing that I would like is to close this issue and then talk about the more editorial part. So the thing is, we had the discussion about how much to mix this with accurate ECN, especially for the SIN, right? The SIN is much more problematic than this one. From that perspective.
Even for the SIN, I think we could reopen the discussion, because I've seen, as I said, I've seen crazy things here. So why the hell do we really have to care about an ECN mark in the SIN? This is really something I think we have to start to discuss here in this working group.
What? Sorry, I didn't understand your comment.
Why do we have to care about a single ECN mark in the SIN?
Why do we need to care about?
Yeah, why does this matter?
Because if the SIN gets lost, you don't get new connections.
No, but why do we have to care about transporting the ECN signal if it got marked? Why do we have to care?
The congestion signal,
Yes,
you mean?
Exactly, because this is a...
So I think you have the person who is going to answer that right behind you, all right? I mean, the thing is, and I agree with her, she has made a very clear statement that is an architectural statement that you should not avoid responding to explicit congestion signals that you receive. It's a bad practice. I actually subscribe what her statement, right? I mean, if you get the signal, it's not okay to just don't
I've
do
heard
anything
this
about
week
it.
discussions that it's okay to ignore loss. And so that's why I'm asking that question. Why does it matter?
But people don't agree that it's okay to ignore loss, right?
Well,
there are a bunch of people, there is a particular people doing it, but people don't seem to agree.
Yeah,
that's
but
a good
let's
option.
open the discussion here. If this happens in another working group, whether we have to care about a single ECN mark. And my statement is no.
Okay, so I will let Mia to respond to that.
Yeah. Go.
Okay. That was on Gori Fairhurst. That was uncanny, because my review, which I'm going to try and send to the authors, and I haven't yet typed it in, came up very similar. It seems the document was complicated because we have accurate ECN and not, and I wonder whether we've set the bar subconsciously high in terms of quality and responding the right way, and made a really difficult document to parse when the concept is very, very clear, but it's difficult in the document to read. So do we really need to intertwine it with accurate ECN?
No, but the problem, I disagree that.
Yeah.
I disagree that accuracy, supporting accurate ECN is what complicates the problem. The problem is complicated in some specific cases, like in particular in this case. All the bias about the negative feedback. This is not a problem of accurate ECN. This is a problem, right? Accurate ECN actually provides you more information that allows you to do a better solution to the problem.
Accurate ECN is fine, and we have to do updates to implement this. We have to do updates to implement accurate ECN. Can we roll the two into one?
Yes.
Okay, then we don't have to just focus on the case where accurate ECN is not enabled, because we don't have to do the stuff. Let us just think about the accurate ECN bit, but Mira's going to talk about that. So I was only bubbling up the same thing and saying I'm at the same level as Michael, I think.
I'm not sure I understand what you're saying. You're saying that we need to drop all the parts that are not accurate ECN?
I'm saying that might be a possibility. This document should be easier to read. It is a thing we want people to do, and it's quite simple. So either we say, just use accurate ECN, and then do this, because that makes it all as simple as one update. I'm okay with that if that's the right thing. Or somehow we make it simpler, because the current text is hard to pick out what really you have to do. Not a criticism, but it's just a
No,
hard
no,
document.
no, that's fine. That's fine.
Mia Kulevin. So I agree. I think it would make the document simpler if we would only use accurate ECN, if we only discuss. So that's a little bit the opposite from what Micah says, but I think that's actually the right thing to do, because first of all, we want to deploy accurate ECN. We want to deploy accurate ECN as a replacement to ECN. It's a change, so we can do these two changes together, and it makes it much more safe.
So suddenly, in the initial proposal from Michael makes much more sense, right? Now, it may make perfect sense to actually have two documents back to back, one without accurate CCN, the other one with accurate CCN, and both of them is simpler to read for whoever wants to read it.
No, so I want one document where, so the document already says if you put a marking on the SYN, you have to negotiate accurate ECN, right?
Yes.
Right. So what I'm saying is only if accurate ECN is negotiated, then you should further think about marking control packets. If accurate ECN is not negotiated, you should not mark any control packets. And that makes the document very easy.
I may agree with that. I mean, given that probably the most important packet is the SYN that you want to get marked, and you only can do it with accurate CN. So you must just as well go for and just do it for accurate CN. I'm okay with that.
Well, just for the record, I don't buy that argument, but I might be in the rough consensus.
Which argument?
I don't buy the argument that for the SYN, you really need accurate ECN.
No, you don't. No, you don't really need accurate. I agree. I mean, as of today, what the draft says is the solution for feeding back the congestion signal to the sender is using accurate ECN, because we don't want to waste more bits and blah blah blah. There is a bunch of arguments in there, right? You could try to do something else. I agree.
So that's more the second point. Like, do we actually care about a SYN being marked? Like, there is an indication of congestion. Do we need to react to it? Is it important? That's your question, right? So the difference between ECN and loss is that's an explicit signal. So there is congestion. For loss, you never know for sure. You don't know why the SYN got lost. You don't know if it's congestion. You don't know what it means. But you also have a timeout, right? If your SYN is gone, you have to wait for a while. So there is kind of a penalty, if you want to say it, but it's also kind of, there is a time where you don't sense anything on the link, and so the congestion might resolve. In this case, you get an immediate signal that there is congestion. So just not reacting to it is just ignoring it is wrong. What the reaction is also a different question.
Well, I mean, as I said, I mean, conceptually, theoretically, you're right. In practice, what happens at this IETF tells that this is a totally stupid conversation if people don't react to loss, which is clearly a congestion signal.
So okay, okay. Let me suggest a way forward. So I understand we all agree that if there is accurate CN, what is written in the draft is the right thing to do. So what I would suggest is let's limit the scope of this draft to accurate ECN. If someone wants to do this for something other than accurate ECN, please write a draft and do it, right? I'm doing this for accurate ECN, and whoever wants to do something else, it's perfectly fine. It's open. It's not incompatible with this. It's perfectly fine. Yes, go for it, Bob.
It's Bob, co-author. The whole issue is, though, that there are two ends. And sort of, I think most people in this room know that about TCP. And so the way the draft says it is, you should only put ECN capability on the SYN if you implement accurate ECN, but you still don't know what the other end does. Right? And then if the other end comes back and says it doesn't support accurate ECN, then it says behave conservatively. Now, we're still going to have to say that, even if we say you only do this.
Right, but we also say that
that's where the complexity comes.
No, Bob, because we also say that, for instance, doesn't matter if any of the endpoints support accurate ECN. I don't know, retransmission, you should mark it anyway, right? And that doesn't matter whether they are or they are not accurate ECN, right? So basically, what I'm saying is let's drop all that, which is really minor part of the text.
Yep.
Just keep the case that it's accurate ECN. The sender is accurate ECN, right? We deal with all the compatibility of the other endpoint, of course, right? But we drop all the part of both endpoints being non-accurate ECN, right? The sender being not accurate ECN. And we
Right, yeah.
we explicitly said that this only covers the case of the sender being accurate ECN capable. And we don't talk and we don't mention, I mean, and the how the behavior is for an endpoint that is not accurate ECN is unspecified, and whoever
Okay,
wants to specify that can do it.
Yeah, we can do that.
Would that
And then-
work?
Then the second response to Michael's point, I'm reasonably okay with being a bit more liberal about responding to loss, you know, and rather than treating each one as sort of each loss is sacred and all the rest of it. However, very much different on the SYN. Absolutely no non-response to loss on the SYN. I will fight tooth and nail to stop that, because the internet collapsed because of that, and it can do it again. And there are people here who are saying, oh, we might even see an internet collapse and then we'll get more research funding. Yeah, right. Now, and the reason is that if you, the back off on the to loss on the SYN is what stops new flows coming into the network, and that's what causes collapses. We mustn't forget that.
Well, again, my comment is on the ECN mark on the SYN, not the loss. I mean, for the loss, we all agree. So, but the key question is, so why to care about an ECN mark on the SYN? And my point is, I don't really see the point. I mean, if the router is really congested, he will drop the SYN, and we're done.
I mean, it's not that we're saying anything. We're just saying what the response has to, is for an ECN mark on the SYN. It's not. We're not being.
So let me see if we agree on the way forward. So we're going to limit the scope of this draft to accurate ECN. And the case where non-accurate ECN sender is not going to be considered, is going to be left open for further future specification. That make everybody happy?
Any other objection of this idea? No. Okay.
Thanks. Next slide. I hope I don't have any more slides, but okay. So, okay, this slide doesn't really apply anymore. So I will change the text to reflect what we discussed and send it to the working group for consideration and see what happens. Okay, thanks.
Thanks so much.
And Gori, I promise I will type my review up, although I won't dwell on that particular issue we've now discussed. I have a few other points which might help.
Okay, thank you. My next presentation, please. So this is a presentation regarding some measurements that we have been doing regarding this experiment. So this is accepted to appear in IEEE Communication Magazine soon. So, but I'll have a link at the end of the slides with a version that you can download in case you're interested. Next slide, please. So what we wanted is to see if we can actually do some measurements to get some initial data for this experiment. And in particular, what we're looking for is to find out whether ECN market TCP control packets, pure acts, are treated, and pure acts are treated differently when they are ECT mark, are differently than ECN mark data packets. Sorry. So basically, what we have done is we started a measuring campaign to see how ECN mark or ECT mark data packets are treated by the network to get some ground truth, some baseline, and then measure how TCP control packets that contain ECN marks are treated by the network and compare the results, right? So that's basically what we did. Next slide. So in order to do this, we use two measurement platforms. One is Planet Lab, that I guess you all know. So we use 54 Planet Lab nodes in 25 AESs and 22 countries. And the other platform that we use that you may not be so familiar with is a platform called Monroe. That basically is a platform that allows you to do measurements in mobile networks, right? So this basically what the Monroe platform has is Monroe nodes that are devices that you can program, that you can put some measurements in there, and they connect to one or more providers through SIMs, right, to mobile providers, and you can execute measurements against servers that you have on the internet, right? So in this particular case, we have 11 ISPs, which are the ones that I show here. Next slide, please. So the experiments that we did basically was, as I said, getting data packets with ECN code points and getting the different control packets with ECN code points and see whether they are treated in the same way by the network or not. Right, so what we tried is all these type of packets with all possible ECN flag combinations, right, including both in the TCP and the IP header, both for basic ECN, ECN plus, ECN plus plus, and accurate ECN. So the tool that we use is we use Tracebox. That is, I'm not sure if you're familiar with this tool. This is a tool that the people from UCL Leuven has developed that is basically like a trace route that increments the TTL. But in addition, what it does, it compares the flag from the original packet to the pieces of the packet that you receive in the error, in the TTL expired error. So that allows you to see at which hop flags has been changed, right? So we executed this from the Monroe node to Alexa 100K servers, and from the Monroe node to our own servers. In this case, we actually control both endpoints, and we can play with, for instance, the CNAC. Next slide, please. We did a measurement campaign between January and May of this year. We used two ports, 80 and 443. We did 25 million measurements, blah, blah, blah. Okay, next. So what have we found? So the first thing that was kind of surprising that we found is that for the data packets in particular, but also for the other control packets, but for the data packets, ECN, regular ECN, we found that 7 out of the 11 mobile providers actually clear the ECN field when you send ECT mark packets. So that basically means you send ECT 0 or 1 mark packets, and what happens is that the first hop of the mobile providers actually clears the ECN fields and turns it into non-ECT, right? Because we found 7 out of 11, which seems quite a bit, we tried other few mobile carriers. We actually tried 7 more, and we actually found that 3 of them have the same behavior. Yes.
Ingemar Johansson. I was going to try to clarify, is that the uplink packets from
yes.
them?
Yes. So and packets going from the client to the server. In the other direction, we actually did not observe this behavior.
Okay. So it is not necessarily the it's not necessarily the mobile service providers that are cleared. It could be a modem chipset.
Sorry,
it could be the modem chipsets that clear the ECN bits as well.
The modem chipset, but it's in the first hop.
Yeah, it's the first hop. I thought to.
So the modem chipset is usually you decrement the TTL.
Yeah.
Or it could be before the okay.
Stuart Church, Apple. If I understand the question correctly, you're speculating that maybe the mobile phone handset itself is clearing its own ECT bits before it sends the packet. But if it's succeeded in 4 out of 11 mobile providers, that suggests that the handset is not clearing its own bits.
Right. So it is the same. Sorry. So I understood the question now. Sorry. So it is the same device that is actually using for the different. The same. The nodes are all the same, right? Okay. So we found. So we also find that is one mobile provider that only clears it in the port 80 and not in the port 443. This is a case of a proxy. And as I said, we didn't find evidence of clearing the ECN fields in the traffic from the servers to the client. And for those who didn't clear, we find evidence of little bit of clearing, 0.53%, which is somehow similar with the current literature on the fixed networks, which in this case for the PlanetLab nodes, we find 0.23% of clearing deeper in the networks, like 5 hops away or something like that.
Okay.
Okay.
Just to make sure it's not a comma, it's period, dot, right?
Sorry?
Zero, not comma, right? In your text.
Well, I usually use comma, but yes, point dot. 0.53. Yes.
0.23.
Yes. So, comparing ECN and ECN++. So what we did is we tried, as I said, ECN and ECN++, all possible flag combination. And what we observe is that they do not cause any packet drops, right? So you don't get packet drop because you set any of these flags, which I guess is a good thing. And the main conclusion probably for this draft is that ECN++ support is exactly the same as ECN+, as ECN. So basically that means that if you get clear, you get clear both in control packets and in data packets. If you don't get clear, you don't get clear for none of them. So basically it doesn't seem to matter. The boxes that do this doesn't seem to look whether it is a scene or a control packet or a data packet. Basically everything works the same, right? So probably from this limited set of measurements, we can basically say it is probably safe to, or as safe as ECN to deploy ECN++. No, just go back. Yes,
yeah.
Miriam.
Quick question. So did you also test this on not mobile networks?
Yes.
Okay.
So I tested so we use the 54 PlanetLab nodes that are fixed, and that's what we use. So another result is 61% of the Alexa top 500K supports ECN, and only 3.51% support ECN+. However, interestingly enough, none of them respond in the way it is defined by RFC 5562, right? So we have not been able to detect any server that is actually implemented what it's in there. So they actually do respond to with Synax, with ECT in the Synac, but they do not behave in the way that it's supposed to behave. Okay, so Bob already reported this before. Next slide. Yes.
Sorry, what does RFC 5582 or what was it say?
What does it say?
Yeah.
So that's a
Yeah, okay, sorry, I didn't want to embarrass you. I was like, maybe you know better and I don't have to read it. I read it.
So actually 5562 defines a very weird behavior, right? So basically says if you receive a mark a CE mark in the Synac, correct me wrong, Bob, if I'm getting this wrong. I think what you should do is start over again the exchange, correct? So you need to resend the scene without and see if you can actually get a Synac back without the mark, correct? That's what it says. So you end up with like a 5-way handshake.
Do you want to do it, Bob? Anyway, the 5562 was the old Sally document which said how to try and negotiate it, expecting it wouldn't happen, and then falling back and doing it again. So you end up retransmitting and a multiple level handshake rather than just a normal 3-way. Right, Bob?
I contacted the authors to try and find what the intention was of what they were trying to do. The original intention was just to put ECT on the Synac so that you got ECN coverage of that, which is an important packet. But then while it was going through the IETF, so there was an academic paper written on that and all this experiments was done like that. Then when it went through the IETF, there was this concern that it had to be exactly like a loss. And so they tried to make it like 2 round trip times worth of delay, like by bouncing the packet back off the client and back again, and it was all a bit weird.
Mia Kulevin again. Do we need to update that?
So that
Yeah.
we actually discussed that, I think, in the last meeting, and what we said is that ECN++ spec will actually update that behavior. Yes. So other stuff that we found just fast. So we found that all the servers that actually support ECN respond to EC flags in this exactly the same way as they respond to 3 duplicate acts, which I guess is a good thing. And we did some stats on initial window as well, and we found that 51% use initial window of 10, 10% use initial window of 2, 10, 4. And funny enough, 0.4% use an initial window much larger than 10. Actually, some of them actually sends the whole file in the first round trip time, no matter what that is. Yes, Praveen.
Praveen, Microsoft. What is the 14% not applicable bucket, and why is this not adding up to 100?
Sorry, once I didn't.
What is the 14% not applicable bucket?
I don't remember. I think it was other values than 2 and 4.
Okay, and all of this is not adding up to 100%. So
this is, sorry?
All of these are not adding up to 100%. So
I don't remember. Sorry.
It would be good to get the right date on the mailing list, maybe.
Yes, I will.
Okay.
So
Thank you.
next slide, please. So here you have the URL to the paper, but I will actually respond the question in the mailing list. So final remarks. It seems for this that ECN++ is as safe as ECN, so probably that's a good news. There is more work to be done in order to get ECN through. And the question is whether it is relevant that we found evidence of ECN clearing. Does it matter? I mean, it's not that it's dropping the packet, it's just that they are clearing the thing. And the problem is, if you have something like a multiple hop path behind the SIM access, right, that are actually using ECN for something, that signal will get lost, right? So any potential benefits that you may obtain, like smaller buffers, smaller queues or anything like that you have implemented before the cellular access, like for instance, if you have a router that is using a SIM or something like that, this will get lost. So this is the impact of actually this ECN clearing. Okay, and as I said, the paper can be found by that. Sorry for not being able to answer Praveen's question, and that's it.
Thank you. Next, accurate ECN.
Before we move on,
Comment on
I wanted to, Marcelo, I wanted to make a comment on that. I'm wondering what it is that you're hoping to achieve with this paper, because titles and how you present things have a big impact. And journalists love their clickbait titles about how the world is coming to an end, and the vegetable that may be killing you. Tune in later to find out what it is. Your title is bad news for ECN. And what I'm concerned about is there are many, many people who will not read the paper, will not read the slides, will not remember where they even saw it, but they'll just remember that, yeah, ECN has failed, bad news for ECN, not safe to use. And if that's the message you want to send, which is like, forget about ECN, it's not worth trying, that's what your headline says. And I'm concerned when I'm talking to my management chain at Apple, right, if my VP says, yeah, I saw something about ECN is not safe. 7 out of 11 mobile operators drop your connections if you try to use ECN. And he won't remember where he read it. He won't know the facts. He'll just have like internalized this idea that ECN is bad. So that's my feedback. If we actually, I would call this title "Fantastic News for ECN, completely safe to use 100% of the time, causes no broken connections." And if those mobile operators want to upgrade their networks to suck less in the future, then that's even better news, right? So I would cast this as good news, not catastrophe and calamity for ECN.
Praveen, Microsoft, I would actually concur with what Stuart said. This is actually good news because I'm going to present later about TCP Fast Open, and here the failure mode is just removing the bits, right? It's actually very safe to deploy and make incremental progress on versus some of the other things we're trying to do with TCP. So I would also classify this as actually very good news.
Okay. Right. I guess I'll respond on behalf of us both and say, well, think about that. Yeah. I'll respond on behalf of us, the co-authors, and say, well, think about those comments. Yeah. Right. Accurate ECN. There's the co-authors, and we've got changes in affiliations. Next slide. Right. I'm not going to go through the recaps. This is just in the slide pack for those that are new here, maybe, so they can read these slides in their own time. Next. Again, a recap of the solution, which I'm not going to go through. Next. Right. So this follows on from the previous talk, and I asked for the agenda to be changed so that they would follow on. In order to respond to the measurements that we've just heard about, we have altered the accurate ECN draft. We've actually taken stuff that was in an appendix, waiting to see whether measurement studies would find problems like clearing ECN, and we've put it into the main body of the document now because there are those opportunities, they're not problems, right? And or issues. And so what we're proposing is, if you just look at the picture rather than the words for a second, is to have full feedback of what was in the IP layer on the SYN and the SYN-ACK in the TCP header of the SYN-ACK and the next ACK, right? So you can see there the way that goes. So and that means that both bits are fully fed back, rather than just feeding back whether there was a C mark or not. We get full information on what the network has done to the IP layer, at least on those first two packets, right? Now, we could get that information later in the connection by a bit of heuristics and watching what's going on, but particularly because it's an experimental protocol, we thought, let's measure it accurately and report those measurements as part of the experiment. And it also makes the code easier because you've got a clear indication of what's going on rather than having to do heuristics, right? Yeah, that I think summarizes everything on this slide. Oh, other than if you find that the IP ECN field has been mangled, when you get the feedback back of what you sent, then you disable it for your half connection, but you can't, there's no mechanism to tell the other end, so it's a half connection thing. The other end can continue using it, and that's fine because indeed in the measurements we found it was an asymmetric clearing, and so it's okay to use it on one half connection, even if it's broken on the other, right? Okay, next. So the way we've done this, these are the top table was already in the draft. We've added another table for the SYN-ACK. So there are 3 ECN bits used in the TCP header, and we now use 4 different combinations of those to feed back all the possible values. And this is during the 3-way handshake, and it was already defined as being a code point based feedback at that point. It's only when the thing gets started, after you've not got SYN equals 1 on the packets, that you start just having a counter counting the number of C marks. So this is how we do this feedback, and actually the encoding we use had to fit around other uses of them in other versions of ECN. But essentially, you've got, if you look at the numbers in binary, they would be 2, 3, 4, and 6 for the 3 values on the field. So it's reasonably easy to do in the code. We've used the same in the other direction, 2, 3, 4, and 6 for the same code points in the IP header. And there's loads of detail in the draft about how you can still support SYN cookies and things like that. So even if the server hasn't got any state, when it gets this third act back, it will still all work. Okay, next. Right. So that was the main change to the draft. The next main change was to write in the summary of the discussion that we had at the last IETF on change triggered acts. Now there was concern that this might not be possible with offload hardware. What we've done is we've changed it to a must, from a should to a must with a get out clause, because we wanted to ensure the receiver could rely on this behavior. But given it's experimental, we have described a possible experiment that people could do that isn't the must. You know, so it allows people who are having this problem to, it gives them a hint that we're happy to see experimentation on this. And then it says, because of this problem with needing to rely on the behavior, that it's then their responsibility to deal with the other end understanding this behavior. You know, it's an experiment, right? Pardon? Right, it's their responsibility. That's a fact, right? So one and the one possible compromise is that instead of not doing change triggered acts because your offload hardware can't do it, or you'd lose your performance because you can't use offload hardware, to do change triggered acts during slow start and then go to offload once slow start has ended, right? And that means that most of the performance of most of the servers, most of the time, is using offload, and it's just for the slow starts that you're not. And I'm told that there's very similar code to that already in place. Next. Right, we did some minor edits as well. Someone wanted to just check that we weren't relying on a certain type of ECN in the network. It wasn't related to L4S or something, and we made that clear. We added that deployment itself should be an experimental success criterion. We added that you don't use the congestion window reduce signal, so just in case anyone thought you still had to use that. And we also made sure that we defined the behaviors of all unused values so that it would be clear in the future what the behavior would be for forward compatibility. Michael.
Yeah, so this is again Michael speaking from the floor. So thanks a lot for addressing my comment on the experiment success criteria. Unfortunately, I don't like the new wording neither. So I think I owe you something on the mailing list. You still have wording in the document that refers to the TCPM working group. And okay. I think this doesn't address my comment from the last working group, but instead of saying it on the mic, I probably have to write it. Or maybe I have to propose some alternative wording.
Yeah, please do. Yeah.
So regarding the last point, one very naive question. So I mean, this is an experiment. So assume that we move this to standards track at some point in time and assume that we have to change something. How would we negotiate a standards track version?
Right.
I think this is something, I mean, you don't have to necessarily document this in an experimental thing, but it's something that, in my opinion, would warrant thinking. So how would the standards track version of this be negotiated?
Right. One technique we've written into the draft is that the counters start at a certain value, and if they start at a different value, it could imply a different version, right? And we say that the current version should be able to cope with the counter starting at a different value?
Yeah, as I said, in general, I think it requires thinking. I haven't thought about it, but I actually would look for a standard track version of this at some point in time, and this is why even in the experimental design you should foresee that, in my opinion, how the upgrade path to standard track could look like under the possible assumption that the protocol has to change.
So, Mia Kulevin, I think that's not a thing that is only specific to accurate ECN. Like, there are a lot of cases where you have the experimental thing and then some things you can't change anymore, or like it wouldn't work anymore. So like the things that we just described in the experiment are things that we can just change without no negotiation. For example, not using change triggered X, you just change your implementation. So that's the questions we have. I don't think that there's actually an issue here.
Well, if something on the wire changes, some encoding of the bits, for example, I mean, we don't know how the standard track would look like. It's an experiment.
I know.
So that's why, as I said, I think I don't understand it. I've not looked at it. I don't have a solution. But as I said, I mean, at the end of the day, I mean, this consumes a bit in the header, which actually should happen on standard track at the end of the day. So we have to think about the upgrade path, in my opinion, early. You don't have to document it at all costs in the document, but I think it's something that you should at least keep in mind. So
yeah, I mean, the response I gave you works fine. It's like a version number. The only problem is it relies on the option being there, and if you know the standard track version doesn't have the option and it only uses the 3 bits in the header, or the middle box has stripped them or whatever, we can do very little with 3 bits because we've you know we've used as much as we can out of those 3 bits, and we can't do much more. You know, yeah. Okay, next. I think we're done. On the next slide is so yes, it's been implemented in Linux. It's all the open issues that were written into the appendices are now closed. We've deleted the 2 appendices, so we believe we're ready for working group last call. I don't know whether you want your edits done during RFC, you know, a later stage, or whether you want them done before the working group last call. But we're certainly willing to do them.
So yeah, you just submitted the draft just 3 weeks ago, right? So we have to review it to some extent.
Yeah.
Yeah. And after that, we will think about how to proceed the draft. Oh. Yeah. So basically, this draft has been submitted 2 weeks ago. So someone need to review it
Yes.
before we go to the working group last call. So if anybody want to volunteer for reviewing, that would be really great.
Couldn't they review it in working group last call?
Yeah. So I mean, this has been around for a while, but I think we have seen a lot of reviews over the whole time of the lifetime of the document. So there will be additional reviews in the working group last call. So let's just start it and get those reviews in.
Praveen, Microsoft, I would volunteer to review this. And I think this is useful work. We have been trying to get ECN deployed on the internet, and this is, I think, a step in the right direction. I had a question on one of the slides where you said about something about hardware offload. I'm assuming you're talking about like full TCP offload to the hardware.
Yeah, it's the point is that the acts, like with DC-TCP, in fact, are triggered by a change. You have to send an act when there's been a change.
Yeah.
And that has some people have complained that makes hardware offload difficult.
So my understanding is that full TCP offload has not really been widely deployed, if my understanding is correct. The other point I would make is this is some of these issues are relevant to LRO as well, and it would be nice to call that out in the draft, because at least when Windows does LRO, we specifically required that when the core point changes, you don't actually group those packets together.
So I didn't. You said it's relevant, and I didn't catch the word.
LRO,
right,
yeah.
LRO.
So I think we should make a statement in the draft about that, and I would be happy to give you the information on that, on how we specify the rules for that for the coalescing engine. Thank you.
Okay. Yeah, Praveen, thanks for volunteering reviewing. Thanks so much. Vidya, you want to say something?
Yeah, mere equivalent. So the offloading case, I think that's mainly egg aggregation cases.
Can you be close to the mic?
The offloading case, it's mainly egg aggregation, where the hardware decides to not send out all the eggs, which was concerned. And that's like specialized hardware that is used in like whatever storage networks and stuff. Not sure if that's a real concern for like a general purpose implementation.
Okay, so I think this stuff is getting matured, but we still need to get some reviews. And then also one of the chair will take, look, detailed reviews. And after that, we think about if we can go to working group Rascal.
Okay. Is that likely to be between IETFs or the next IETF or?
Something.
Yeah. Okay. Right. Thanks.
Hi, Lars Eckert. So this is not on this draft, but it's more on a general topic of ECN. So we do quick, right? And Ingemar is actually leading a group of people to think about how Quick can benefit from ECN information. And I actually care way more about Quick than TCP these days. So I think if the ECN people wanted to make an impact and wanted to make an impact quickly, you should look at Quick because it's going to push a lot of bytes in a very short amount of time. You can keep looking at TCP too.
Okay.
Yeah. I'm involved with the Quick thing as well. Yeah.
For those of you who are already involved, you already know about this. I'm mentioning for the people who might not be involved in this yet and might want to get involved, because I think Ingemar's team could probably use some help. So Quick is incredibly pressed for time. That's why we break off all of these things into little, design groups that can work out a proposal for the group. And if you want this to go into V1 of Quick, which will hopefully ship sometime next year, it needs to be ready sometime next year. Which is not necessarily a time frame that is very, normal for the TCP folks.
Praveen, my question is for Lars, actually. Like, is this in scope for V1? Is this in scope for V1 of Quick?
So, if nothing is ready, right, it's certainly, there's no point in having a discussion. If somebody had a proposal and there was some evidence that it might be useful, we can certainly talk about it, but without anything to discuss, it won't be. If there is something to discuss, it might be.
Just to give some specifics, if those people that are interested in what Lars has just said about adding ECN to Quick, there's forming a design team meeting at 4 o'clock this afternoon, I believe, in some room beginning with H. And if I can't remember how, I don't know, but anyway, if you look at the Quick mailing list and look for Ingemar's mail, it will tell you.
Okay. Yeah, thank you so much, Bob. So next will be RAC TCP. Yuchen, are you in the Meet Echo? Can you hear me, Yuchen?
Hi guys, can you hear me?
Yeah, I think I can see you, hear you.
Okay, good.
And can you see my slide?
Yes, I can. Yeah. Okay. Hi everybody. I'm Yuchon to present RAC update. And this is work with my colleague Neil Carwell, Nandita, and Priya at Google. Next slide, please. So just a quick recap of what RAC is. So RAC essentially is a time-based detection of packet loss compared to the old do-back threshold we all know about. And the best way to describe RAC is that conceptually, think of that every send packet has a timer, has a timeout. And this timeout is constantly adjusted by all the recent RTT samples collected from X, stack, either the packet sent before you or the packet sent after you. And then basically, the timeout is set to about RTT plus a reordering window. And if I can translate that into a do-back threshold, is that the reordering window simply becomes 0 if you have more than 3 dewbacks. And you can sort of have a sort of a dewback threshold equivalent implementation of rack in that way. And the implementation takes care of how you don't really implement a per packet timer, and that's really the details that doesn't need to be presented here. But the basic idea is every packet is retransmitted after RTT plus some window, some settling time. Next slide, please. And the other thing is tail loss probe, because with rack, you still need some ACK in order to trigger the recovery. But sometimes you don't get the ACK. And the idea of tail loss probe is, well, if you wait a little bit and you don't see, instead of this long conservative timeout, instead of just reduce window to 1 and then declare everything is lost, you send a scoped a probe packet out after an RTT or 2 to trigger some ACK information, and that ACK information will tell you either, okay, the probe packet has been delivered and along with other packets, or the packet has been lost. Of course, there is always a possibility the probe packet is also lost. Then you wait for this 4 long timeout, and then you declare everything is gone, like the whole inflight is gone. Even the scout I have said is get killed in the field. And the whole idea is you have this quick timeout, just send a little bit of traffic to see what's going on so you can react quickly. And that's the essential idea of TLP. Next slide, please. So quick status update, Linux upstream, Google, Netflix, Windows all use RAC TLP by default. Another one that's is also quick. But currently, they all use RAC as a sort of additional mechanism to the classic dewback threshold rule. And I'll talk about how we plan to retire dewback threshold if we can. But before that, I'm gonna talk about the major changes, since IETF 98, how we optimize paths with very large BDP and also frequent reorderings. And we found some, kind of again issues with middle boxes not setting the sequence right. Next slide, please. Next slide. So first thing we found is the large BDP paths. So this is a snapshot of this graph taking from Google Cloud Transfer. This is RTT is 300 millisecond and on a 10 Gbps link. And this cloud user is using Cubic in that case. And you can see that as it's slow starting, getting faster and faster, then he starts seeing some losses, actually quite a few losses. So the white line here is the data line. The green line is the ACK line. And all this purple stuff is the stack packets that's getting received and captured at the TCP dump at the sender. And you can see that, okay, very quickly it starts retransmitting packets, which are marked as red color. But it seems like it's retransmitting extremely slowly compared to what it has been sent, right? That doesn't quite conform to what Cubic is designed, because on losses, it reduced the rate or C-win by about 30%. But it's sending a hell lot slower. And of course, this is being reported. And so what happened? So on the BDP like this, you got about 385 megabytes of BDP, which translates to about 257,000 packets in C1, right? And then we're talking about even this congestion control working very properly, which has a C1 relatively close to the BDP. And but the Linux stack and RAP processing engine is essentially scanning a linked list with some hint pointers, which basically he assumes that, okay, the next stack is usually somewhere close to what my previous stack is in terms of sequence space. But on heavy losses, and especially when you have second order losses, that means your retransmit get lost again. then it's having issues because it has to reset this hint pointer, so the hint pointer don't work that well anyway. And the worst case we know is essentially ON. And what happened is the CPU is completely saturated by processing this ACK. Every ACK comes, scans this humongous queue, even with a lot of optimization going in, and is simply not able to retransmit fast enough. And most of the work he spent is completely sort of duplicative, because it's like, okay, I have to scan all this, large queue, same queue, but all I found is, oh, there is one new packet that needs to be retransmitted. So it's really dumb. And essentially, this is not a protocol issue; it's simply an implementation issue. But it's doesn't really happen in most of our daily transfers. It only happens when a cloud user, which is smart enough to use a much higher receiver window, because the Linux default receiver window is only a couple megabytes. So most of the case, when you use that, you will never see it because it's all receiver buffer bottleneck. Next slide, please. So what we did is really just implement a better data structure for stack scoreboard. Instead of a linked list, we changed that to a RV tree for all login words tree, and that improves a lot. And the other is RAG processing. So RAG processing needs something more than an RV tree or anything, because for RAG, all it cares is about the time. Either you send a packet or retransmit a packet. It's all about when you send the last, what's the last time you sent the packet. So you need to build a list that's sorted by the last transmit time. The good news is that it's a constant time to maintain this list. When you transmit a packet, you take it out from the queue and you stick it to the back. And when the packet gets stacked, you simply remove it from the queue because you no longer need to care about it. It has been delivered. Only in case of stack reneging, you need to rebuild this list, but it happens very rare. So then for every ACK that comes, RAG only needs to look at the packet that was sent before the most recently ACK packet, right? So that's usually is looking at 3 packet, 4 packet, 10 packet at most. It's rarely that you lose 10,000 packets in one shot. It doesn't really happen that often. So both optimization has been implemented in the upstream Linux, and it really reduced the stack processing overhead by a large factor, and feel like TCP is now more equipped for super large transfers. Next slide, please. So another challenge has with frequent reorderings. We haven't seen this in real life network yet, probably because TCP isn't really reordering robust yet. So this is really a fabricated case. We just want to stress test how RAG will do under very frequent high degree reordering. So here's a test we conducted on 100 Mbps. Link was we sort of randomly delay the packets between 15 to 25 milliseconds. And you can see that this is using the BBR congestion control. And again, a lot of SACs, frequent reordering, and a lot of red, that means retransmit. The only difference is that all these retransmits are spurious retransmits. These are not real losses. So these are just spurious recoveries. And the reason for that is that the current version of RAG uses a static reordering window, which is min RTT divided by 4. And in this case, the reordering window is just too small, right? So you get reordering outside that window, then you are screwed. RAG will just tell you this package is lost. So even TCP Linux TCP has implemented this thing called see and undo, or TCP iFail, that you can detect spurious recovery. It can really help in this case, because sure, you detect, oh, the loss recovery I just did was false, so I revert the sequence. But what happened is, after you revert the sequence, the very next act, you enter recovery falsely again. So instead of probing the bandwidth and making forward progress, all you do is you keep breaking the TCP. You know, you hit the brake, you lose the brake, then you hit the brake pedal again. And TCP is never able to really ramp up to 60 megabit. It only gets to 50 megabits per second. And the situation will get worse if the RTT gets longer. This is not specific to VCR. We can apply qubit as well, and it's essentially the same problem, because congestion control is simply not functioning at all. So the next slide, please. The solution is not too difficult, as you can imagine. We need to make the reorder window matter by adapting it. Now the question is, how do we adapt? How do we know the reordering window is too small or too big? And we did some survey. I mean, we could have used like a timestamp that would help us detect spurious recovery. But we choose DSAC in the end because DSAC is supported by Linux, Mac, and also Windows. And it has been supported for a very long time for all these 3 operating systems. And so that's good. That means, you know, most of the receivers that support this, we can have proper feedback. So what is DSAC? Maybe not many people know that DSAC is just, you know, when you get a spurious transmission on the receiver, you simply tell the sender that, hey, I received this sequence range again, and please stop sending me this. I already got it. And the algorithm is pretty simple. Let's say initially we set the reordering window to a quarter of the mean RTT. Then for every round trip that we see some DSACs, that means, okay, you have retransmit something spuriously. Then we just sort of progressively increment that up until, you know, to SRTT. And we don't want to make the reordering window too large because the rack is really designed to deal with sort of reorderings with an RTT range. So that's why we have the upper bound here. So then we will keep this sort of larger reordering window. Of course, you always want to, how do we discover that now the reordering window is too large, right? And the simplest way we can think of is, okay, after some A-half value, 16 DSAC-free recoveries, then you reinitialize the reordering window, and then you try again. And we think that's sort of acceptable, and really the intention is to not make the algorithm too complicated and just trying to keep it simple. And here is the exact same test that we run with this this new adaptive reordering window algorithm. And you can see that initially you still have some spurious retransmissions, but eventually the rack reordering window will, you know, get big enough, so you start making those mistakes of spurious retransmission. You still get a lot of sacks because the reordering is still happening, but the reordering window now is big enough to prevent you from doing that. And if I can extend this, really zoom out of this graph, you will see that after a while, it will repeat this process because it has reset the reordering window. And then, of course, it's gonna have the same issue. But I think it's sort of a balance between keeping it simple and then getting a little bit performance penalty once in a while. A question could be that, okay, so we have this reordering window based on DSAC. Why don't you just measure the reordering degree directly in time The problem is that it adds quite a bit of state because in Linux, when a packet is stacked, right, it's glued to a previous packet that's also stacked in order to keep the memory pressure small and to speed up all this stack processing because stack blocks tend to be continuous as the act comes. And this makes keeping the time in the stack blocks quite complicated if you need to track, okay, for the two merge stacks, what's sort of your time of individual time that gets stacked. So that's why we decided to just try this simple approach to make it effective, and seems to work okay. Next slide, please. So now we have to deal with middle boxes. That's actually reported on the Linux development list. People are finding out, hey, my TCP is not making any progress, and that's the time sequence. It keeps sending TOP probes, but nothing is really getting delivered or anything. And essentially, the connection just hangs. So what happened? Some middle boxes we wrote the TCP header sequences, but he forgot to do that for the stack blocks. So what happened to this TCP connection is a TOP is triggered and of an ACK. We arm the timer, and that TOP probe solicited ACK that has the right TCP header sequence, but the wrong or invalid stack sequences. And as a result, TOP wasn't really able to parse it because it's considered an invalid ACK. So he armed the timer again, and then basically the story repeats it forever. So we of course have to do some mitigations just to make sure that if you are receiving an invalid stack, really you have to break this loop. And that kind of works out. It's not a complicated change, but it's just what happens in real life, even when you are doing all this probes.
Is it possible to ask a question?
Sure, yeah.
What was invalid? Is it just random numbers in the sequence space?
Yeah, so
it's
not random number. So essentially, this middle box is applying an offset that he kept for whatever reason to the sequences. Yeah, but he doesn't do that for the stack. So you can see the stack sequence here because it's all just, you know, by offset by some random number that middle box is doing. Yeah. Next slide, please.
Well, SAC is so new, you couldn't possibly expect a middle box vendor to have heard of it.
Okay. So next steps, I think our vision is really make TCP resilient to reordering. I mean, certain degree of reordering, and trying to keep the loss recovery simple by using the time information. I think this enables some ideas like flowlet or fast forwarding. Like you don't need to keep a reordering buffer that much in the routers. And the next working item is to say, can rack TLP be a standalone recovery mechanism, and without using this dewback threshold? So that's what we are working on and doing experiment to say, if I don't use the dewback threshold and to trigger fast recovery, do I really receive any performance penalty? Because intuitively, you will have performance penalty, right? After 3 acts, fast recovery starts, and you are saying that, okay, we have to wait a quarter of an RTT. So, but even if we have to use the dewback threshold, it's actually trivial to implement in rack, because all you do is you introduce a conditional test to say, if I receive 3 dewbacks, set the reordering window to 0. That kind of thing. But this is something we're experimenting, and we hope by next meeting we'll have more data about it. And of course, the next thing I really owe the community is to update the expired draft. So this is all just in the presentation. Nothing. This update is in the draft, and I will try my best to do that. This month. Okay, that's all for my presentation. Happy to take questions.
Questions?
Praveen, Microsoft. So you said that the reordering problem was theoretical. I wonder if you have any data showing what's the highest reordering degree you have seen in practice. I understand the need to make it more resilient, but my understanding is that we go out of our way to make sure that TCP packets don't get reordered in the network using ECMP and making sure, using RSS that we process all the packets on one core. So we actually try very hard to minimize reordering. So I'm wondering, is that data showing that this is a real problem?
Yeah, great question. So on all the tests, on all the connection that have been looking, it seems that a quarter of RTT is fairly sufficient. And even on the key is really, let's say, for most of the cases, the reordering is caused by parallel forwarding, and these are like links of very similar delays. But we start seeing problems if people are trying crazy idea like a packet spray. Okay, I want to spray across all the 27 links I have available from A to B, and the reordering could be in this case beyond a quarter of RTT. So, and that triggers us to say, okay, we need to prepare for this kind of cases. But right now, the short answer is I haven't seen reordering that's that a quarter of RTT cannot handle well. Yeah.
Okay, thank you. The other question was, so replacing rack TLP as the only loss recovery mechanism. What are your, is there any data showing how it works on really low latency links, like, tens of microseconds? I mean, the problem here is that fine-grained timers are a problem. So I was wondering how we would completely get rid of, DOPAC.
Yeah, I think that's also a great question. I think in Linux, particularly the Google version of Linux, we have sort of the luxury of high resolution timer, microsecond timers. So that's fairly sufficient for a data center, even you're talking about 10 microsecond RTT. The real challenge will come from first, the operating system cannot support these fine-grained timers. Let's say it's still using millisecond timestamps. Then 3-2-back does has its advantage. But I think in most of the data center cases, with assuming powerful servers, rack is in my mind probably is just as fine. Let's say the RTT is 10 microseconds. Let's go to the extreme, 10 microseconds. The rack fast retransmit will start about with the current setting 2.5 millisecond, 2.5 microsecond, and it's all triggered by X, right? So we don't really require a high resolution timer in that case. And I would consider that's almost as good as most of the UBAC threshold, which would trigger probably at 0 microsecond. But the case of that, it's more concerning on much longer RTT links. Let's say 1 second RTT, not that uncommon, right? Then rack would trigger after 250 milliseconds, while dewback might take 3 milliseconds to trigger. So down those cases, rack could indeed be slow, and then we might have to change how the reordering window. It's all about how you set the reordering window, right?
Correct.
And I don't see this as like rack can really advance. Just be smarter about the reordering window, I think we can deliver that. And the algorithm change is simple. It's all about just changing the reordering window instead of having all this different heuristic of how many dewbacks do we really need to count for that.
My only feedback would be that the packet-based detection is actually not that complicated. So having it as a complementary solution is actually not that bad.
I agree.
I had another question. Another question on one of the earlier slides. Maybe it was slide number 2 or 3. Further back, I think. Yeah. 70% of losses recovered via timeouts. Can you please clarify that?
Okay. Yeah. So essentially, on Google.com, a lot of transactions, or you can say HTTP response, is really just one packet. There is not much you can do with one packet in rack. We will send a TOP after the TOP timeout, but it's still, again, it's a timeout. And that's why you can say basically probably 70% of the HTTP response are just all this single packet stuff. Yeah. And that's really the reason.
Thank you.
Yeah.
Ilpo Järvinen. I have also seen similar numbers from other servers. There are these MIBs from which you can see what is the actual reason why the Linux recovery was Linux stack was initiating the recovery, and it's also seems to occur on other people's servers. So this is quite typical number actually. This roughly 70% of the recovery's first indication about that there is some problem is the RTO timer expiring.
So are you saying the reason we have this high percentage of timeout-based losses is there is some bug in Linux stack, or?
It's not the stack problem. It's just that you lose all tail of your window. So and there is nothing new to transmit. So basically, when you don't have anything more to send, you end up always into this condition that if the tail is lost, and it seems to be this 70% is quite close to the number that typical servers get.
Yes, I agree. I have to admit that I think that slide, I literally copied it from the previous slide, which is copied from previous slides. And that number may be outdated. It could be happening. This could be a number I quoted before HTTP2 was actually deployed very largely at Google. And HTTP2 does change that number, lower that number quite a bit, because it tends to uses one connection, and of course the per connection volume, and it does all this pipelining stuff, right? So it's a lot less this sort of one packet RPC change now. I will be happy to update that number as well. But HTTP2 does help this case a lot.
Ingemar Johansson. As regards to this RTT divided by 4 sort of a reordering window, and if you look at the 5G technology with the dual connectivity sort of functions where you can switch the packet transport between a millimeter wave and other frequency bands, and then you can expect to get the reordering depths larger than a quarter RTT. I don't have the real numbers, but I believe it's a good addition to Linux TCP and other TCP versions to be able to cope with a larger reordering window.
Yeah, so I think depends on the network. It's a little bit like IWCAT. It's definitely one size fits all, but you also have to pick a default. And I hope that in the future, we're actually experimenting some other value, like, instead of a quarter RTT, how about an eighth of an RTT? or so. And I was thinking even stuff like, okay, you could have a per route reordering window default to say, okay, if on this particular network route you're really sure I want to accommodate better reordering or be more aggressive about retranslate, you could have configured it differently. Yeah.
Yeah, that could be an option also.
Ingemar, just for the notes, how much sort of reordering did you say? I was typing when you said how much-ish.
I'm afraid to say any number at all. I can't say it right now. Sure.
Oh, that's I recorded it. I couldn't understand what number you said.
Give it a fussy some number.
Okay. Any more questions? Okay. Thank
Thank
you,
you.
Jun. Now we are working on the individual draft presentation. Marcel.
So, Marcelo Añulo again. So, okay, here better. Okay, so Marcelo Añulo again. So I'm here to present this new draft that we submitted about about increasing the maximum window size that can be reached with TCP. Next slide, please. So as of today, the maximum window that the sender can use to send data is determined by the receiver window field in the TCP main header and the window scale option. Actually, the maximum window is reached when the window scale option is set to the maximum allowed, which is 14, which results in roughly a gigabyte of data in the sender window. And that essentially imposes an upper bound to the maximum speed that TCP can send, right? So here's a simple example here. If you have a round trip time of 10 milliseconds and the maximum speed that you have available will be something like 80 gigabits. And there is technology with 100 gig already. Of course, we're talking about a single connection, but nevertheless, we are in the orders of reaching that limit. Next slide. So doubling the maximum window possible is easy, right? Because actually today there is an unnecessary restriction of having the maximum window scale value of 14. The original motivation for that is they wanted to be able to distinguish the old and the new packets. So that basically allowed a maximum window of a fourth of the total TCP sequence number space, where you actually what you need is only to detect whether it's the packet is in the window or outside the window. So basically, you could actually easily increase to the double of this, right? So allowing a value of 15 in the window scale option would be okay, right? And that will allow you to essentially double the value that you have so far. So we proposed this, a year ago or something like that, right? And the feedback basically was, well, if you consider this is a problem, actually doubling will buy you a bit of time, but not really much. So you really should start looking into how to enable larger increase of this, right? And that's basically what we did, right? So we went to and take a look about how to do to actually increase more than this the TCP maximum connection window. And this is this draft, right? Next slide. So if you want to go beyond 2 to the power of 31, that implies that you need to increase the TCP sequence number space, right? Because you need to be able to increase to identify a larger number of packets that will be in flight. Okay. This will be much more painful than the previous approach, right? So this will require additional changes. Next slide, please. So ideally, basically, the idea for this will be essentially to include a prefix of the sequence number and the ACK number somehow in the TCP packet, right? There are essentially two ways you can think about this. Or either you define a new option, that is what DraftLuni is doing, or to repurpose somehow an existing option. Lars.
Lars, tell me why this is a stupid idea, but sort of if you had the bit 15 or
sorry, once again,
if value 15 in the window scale meant multiply all sequence numbers by some factor, would that not do what you wanted? Which means you can't send shorter segments anymore. It comes with all kinds of sort of things, right? But if it just means, multiply everything by 64.
No, but the problem is that, the problem is that you have the sequence number space is, the sequence number today is 32 bits, right? So
yes, but what I'm saying is if bit 15 equals 1 or value is 15 means it's not anymore.
And you need to carry the sequence number somewhere else.
No, you multiply by a constant factor. But I'm probably missing something pretty fundamental.
You need to identify. No. But the thing is, you need to identify the bytes.
Stuart Cheshire, I think what Lars is suggesting, I'm not agreeing with it, but I want to clarify the suggestion. The sequence space would no longer be counting bytes. Yeah. It would be counting chunks of 16 or 256 or 4K. But then you couldn't write a 1-byte segment. You'd have to have chunks of 4K. Yeah.
Right. Yes, that's another way of doing it. Yes, that's another way of doing it. Agree.
Means TCP is not a byte streaming service. It's kind of packet byte streaming or something. It's not byte stream.
Okay. No, go back, please. So, no, next slide. So there is a slide in the middle that you need to stop in there. So go back one. Yes, here we go. So as I was saying is we need to, if we want to extend the sequence number, we need to be able to carry more bits of the sequence number, and the way of doing this is either you define a new option, that is what DraftLuni is saying, or you somehow repurpose an existing one. And we thought it would be interesting to explore whether you can repurpose the timescale and the timescale, no, the timestamp option. Sorry, it's a typo there for this. Okay, next slide. So why we think that the timestamp option is a good candidate for this? So there are two defined use cases for the timestamp. One is RTT measurements, and the other one is pause. If you actually have a larger sequence number space, you don't really need pause, right? So actually, one of the uses of the timestamp option is already subsumed into this new format. Right, so the only thing that is left is you somehow need to accommodate the other defined use, that is the RTT measurement. Yes, Michael.
Yeah, I'm actually referring to what you have further down on this slide, but the timestamp option is one of the options that you don't necessarily need in the SYN. There was a long discussion on that.
In the SYN?
Yeah, the timestamp option is one that theoretically you could negotiate after the SYN. We don't have it as of today, but it's not impossible to do that.
Yes. Okay.
It's tricky, but it's one of the candidates where we could get space in the SYN. So we, as arguing that the SYN space is crowded, and then using the timestamp option. Yeah, I mean, it's not impossible to discuss that, but you could also just push the timestamp option out of the SYN, in my opinion, and do something new.
Okay. Yes. Well, actually, my argument down is not really relevant to the. Well, yes, maybe. So one argument for So let me state this and then we discuss what you just said. So one argument for using the repurposing the timestamp option for this is because you have limited number of space in the SYN, right? So here I have a short list of different options that usually go in the SYN that are considered, I think, useful. And the result is that you almost use most of the available space. And if you want to additionally add a new option that carries the prefix sequence number, you probably don't have enough in order to carry all these existing options and the new option. So what you're saying is that you could actually substitute the timestamp option by the new option, and you don't really need. That may be possible, I guess. The problem is that you actually do need the reason why you actually do need the timestamp option. It is likely that you need the timestamp option in this type of connections, because these type of connections are likely to send a lot of data, so you probably need at least pause if you are unable to get the extended sequence number, right? That's the reason why we think that if you actually can embed both meanings in the same option, you achieve somehow a graceful fallback, because you either end up using either pause or the extended sequence number. That kind of both of them solve the same. I mean, are in the same direction, right? I don't know if that makes sense. And the other argument for using an existing option is that there are some measurements that have shown that unknown options are more likely to experience problems than existing options, right? So actually reusing an existing option, you benefit from the fact that current middle boxes kind of are likely to be more gentle with them. Next slide. So the main problem that the timestamp option has is that it's basically an opaque string of bits that don't have any kinds of flags or bits reserved. So you need to be able to signal that there is some other place, that there is some other meaning in the timestamp option. And what we are proposing here is to use the available bits that are left in the window scale option to signal that the timestamp option will actually carry additional, will be carrying the sequence number prefix rather than the timestamp. The reason why this kind of makes sense is because if you want to benefit from the extended sequence number, you actually need to also include a larger window scale, and this basically will achieve both purposes. Okay. Next slide, please. So if you repurpose the timestamp option to actually carry the prefix sequence number, the sequence number prefix, the problem is how do you manage to still use it for round trip time measurements? And in the draft, I'm not sure it's worth going through all of them, but in the draft, there are several options in ways that you can actually repurpose. You can include both the prefix, the sequence number prefix, and sometimes sporadically timestamp information. Yes, Michael.
So this is Michael again from the floor. So the timestamp option, to the best of my knowledge, is also used by monitoring tools to estimate the round trip time of the TCP connection. This is a widely used thing. So that would likely break, right?
That would likely break. Unless the middle boxes are updated to understand.
This is not really a middle box. It's just a monitoring system that reads the timestamp option.
Well, unless you modify the monitoring system to actually understand which ones carry timestamps and which one don't.
Which means that that monitoring system, for example, has to see the window scale option in the SYN.
Yes.
Which is pretty difficult if it does sampling.
If the monitoring system only operates on a sample of the traffic, which is pretty common for those monitoring systems, it might only see the timestamp option, but it might not have seen the SYN. Yes. Okay.
So you break that.
Yes.
In my opinion.
Yes.
Which is, this is pretty commonly deployed, and it's not it's a monitoring system. It's not a middle box that breaks TCP.
Right.
Yoshi Nishida from Floor. Yeah, basically that's what we'd like to explore. This is experimental RC, so we'd like to experiment how much impact we have.
Okay. So as I said, I have in the draft there are several ways you can actually still encode RTT timestamp information in order to still measuring the RTT. I don't think it's worthwhile going through all of them. Just move on. So next slide. So and next slide actually. So in particular, there is one that would allow. I mean, there are essentially two options here. Either you encode from time to time RTT information. I mean, timestamp to measure the RTT information in the options, or either you. So that basically requires for you to reserve some bits as flags to indicate whether you have prefix information. I mean, sequence number information or timestamp information in the option, or you actually include both of them all the time, right? In which case you basically have less bits. So this is the option where you include you encode both of them all the time, right? So here you will end up with 16 bits for extended prefix sequence for extended sequence number and 15 bits for having timestamps, right? I mean, there is a draft by Brian and Media that actually allows some variable precision encoding of timestamps that will basically tell you that allow you to encode reasonable timestamps within 16 bits, right? So these are kind of options that we have. Next slide. So I guess the first question here is, do we actually need to increase the maximum window available, right? So I think that's the first question for the working group, right? The next question is, do we need to increase it the double or more than double, right? And if the answers to both of these questions are yes, the question is whether this is the right approach or not. But I guess we still need to figure out whether we need to increase the receive window. I mean, the window, the maximum window that is achievable in a TCP connection. That's the input that I would like to get from the working group at this stage, I guess. Any opinion?
Praveen, Microsoft. Today, the receive window, I think by default, we only go up to like 16 meg. And we haven't had like any real customer problems resulting from that so far. So one of the options here would be to just run multiple connections when you hit such a limit. In terms of the approach, I'm not really sure if this is safely deployable. Like we have to worry about SAC and we have to worry about like Yuchung's presentation, like middle boxes rewriting sequence numbers. So anything that tries to modify and increase the TCP sequence number space, I think is a very risky and very difficult change to actually get deployed on the internet safely. So that would be my feedback.
So I am happy to try to conduct a measurement campaign to try to assess some of these problems. I'm happy to do that. There are some things I won't be able to measure, like what Michael was saying. I mean, I really don't know if a monitoring system will break. I guess what he's saying makes sense. I don't know how widely deployed these are. So, but I certainly can. A measurement campaign can actually find out how much rewriting of sequence numbers and timestamps are out there. So I mean, I think we can get some of this data. I'm happy to try to do that. But I guess the first question is we actually, I mean, does it make sense to actually work on this or not? Right?
Yeah, there again, like I'm a bit ambivalent because I really haven't heard this to be a real problem so far.
Lars, so point one, this thing I mentioned earlier, right? Those, when we think about it and see if that would make it easier. The other observation, though, again, Quick. Why do this for TCP? Quick doesn't have this problem. Why do all of this heavy engineering?
Are you a salesman or?
No, I'm serious. I mean, the nice thing in Quick is this is really easy and it's already not a problem, right? So if you have that problem, before you actually have a TCP, before you have worked this out in TCP, you just run Quick.
I'm Goring here. I wonder if Quick already has the problem because it presumably messes up the measuring infrastructure we just talked about. You can't measure it. So I mean, if the thing we're worried about here is lack of measuring
No,
infrastructure.
we're not, right? The thing is worried about is that you're window limited and your performance is therefore limited. That problem we don't have in Quick. Whether the measurement infrastructure is messed up, I would assume that for UDP, they don't even try to look for timestamp flags. So
They can't.
yeah, and that's a known problem with Quick.
Yeah.
But whether or not they can measure does not affect the throughput you're getting.
Yeah, okay. I mean, this will go on
This
for a
is
while,
not
I guess.
Discussion time for Quick and TCP. TCP has a lot of legacy assets. One point.
So this is Michael speaking from the individual floor. So our charter says that we should maintain TCP usability and utility. And that also means that we have to think about certain things, even if another protocol that is not in scope of this here could meet it as well. I think the technical question is, this matters really at high speed, at probably 40, 100 gig, that order of magnitude. And the key question, in my opinion, Bill, if at that speed, for example, other protocols will really work, because for that you need heavy hardware offloading, typically. And I think one of the interesting aspects for something in that space is how it interacts with offloading. And if the offloading for some TCP extension is easier to get than the offloading for some other protocol that I don't understand about. And I don't know that. But I think at the end of the day, the offloading and the question which is easier to implement in offloading seems to me an important question.
So I would like to add the comment about Quick. So Quick does have a little bit of a limited reachability when compared to TCP. So in a general statement that we don't need to improve TCP is probably not okay. This particular problem, I think, is not a real problem because you can always run multiple connections. Is my opinion, but
please make your comment very quick.
Mere Kulevin, I would like to propose a very much easier design. So why don't you just, if you use a higher scaling factor in the receive window, why don't you just also say this implies a scaling window for the sequence number as proposed by us?
To use some of the bits in the window scale as prefix for the sequence number.
No, just say if there is a larger receive window scaling factor announced, that also implicitly means that you have to scale the sequence number as proposed by Lars.
Yes, as proposed by Lars.
Yeah.
Okay, understood. Yes.
Lawrence Stewart, could we use multipath TCP and essentially stripe data across multiple connections as another way of solving this? It's already got 64-bit sequence numbers essentially built in.
I'm not listening what you're saying. I mean, I cannot hear
Sorry.
you.
Could we do this with multipath TCP and essentially striping data across connections, given that they've already essentially got 64-bit sequence numbers at the data sequence layer? That's another possibility.
Yeah, that's another possibility, yes. Okay, thank you.
Thanks so much. Okay. Russ, Praveen.
Hello, everyone. This is a series of talks I've been doing in TCPM just to keep the community updated with what's going on in the Windows TCP implementation. Is this better? So this is a series of talks I've been doing on to inform the community on what's happening with Windows TCP. Next slide, please. So this is a quick recap. So from the Chicago IETF, where we basically we just had enabled TCP fast open by default in the Edge browser in the creators update of Windows 10. We had experimental support for Cubic, rack and TLP enabled for connections which have greater than 10 millisecond initial handshake RTT. And LEDBAT++ was being used for internal workloads. In case you missed ICCRG, I would recommend that you catch up on the LEDBAT++ details. So newer deployment updates. So Fall Creators update is rolling out right now, and Server 2016 has an update as well, which is available for download. And these are the updates that I'm going to be talking about today. Next slide, please. So yeah, so we turned on TFO in the creators update, and turns out that our fallback algorithm was not good enough. So the failure modes actually ended up impacting user experience, and these are some of the verbatim user feedback we started getting from different geographies. So this wasn't limited to like a particular network. This was actually very widespread. And there were cases where the user would turn off fast open and the issue would persist. Next slide, please. So essentially, we had to roll it back. So we had to roll it back on retail builds. Then we decided that the only way to kind of make forward progress is to kind of build our own middle box, which interfaces with TFO, and we call it TFNO. These are some of the things it does. So it drops all TFO segments. It can strip in data, drops in segments with data, black hole the connections after they're established, do some filtering based on source and destination IP. These are basically all kinds of test cases that so other implementers might find useful for testing their own fallback algorithms, which is why I listed it here. And then we worked on improving our fallback algorithm, which would pass all of these test cases and preserve user experience for the browser. Can you go to the next slide, please? So the algorithm that we decided to go for is passive probing. So essentially, we do not want to do active probing. So we are still using user traffic to do this, but we want to be as conservative as possible. So what we essentially do is, the one thing to realize is that to fully determine whether TFO works on a given network, you need multiple connections to the same server. Because the first connection to the server would get you the cookie, but to actually exercise the cookie, you need to go to the same server again. But we did not want to actually open the floodgates when the user starts browsing. So essentially what we do is we only allow one probe connection at a time to proceed on a particular network. So when you connect to a network initially, we would start probing, but then we would not let multiple connections start probing TFO simultaneously. A given probe connection, whenever it's closed, we look at whether there was no reset in response to the SYN, there was no SYN timeout, no full connection timeout, data was exchanged in both directions, the connection wasn't canceled by the upper layer, and there was no sudden RTT increase. So essentially, if all of the following hold, it means that the connection succeeded. But remember that we needed multiple connections. So the state machine actually progresses towards whether we just got the cookie or actually exercised the cookie. Once a probe connection actually succeeds in exercising the cookie, which means it used data in the SYN packet and none of these bad things happened, we declare the network as successful for TFO. If a network hits fallback for any of these reasons, we persist it and we never attempt TFO again until the next operating system update, which means every 6 months this state would get reset and we will start probing again. If a network hits success, then we stop the probing process, and basically for the entire boot session, we would just remember that TFO works on this network. Again, this is us being conservative, that we do not persist this information. So if the network, for example, added a middle box later, which caused problems, we would still be able to back off. So the good news is that Fall Creators Update is actually rolling out worldwide right now. It's been rolling out for about a month, and this is the first retail release where we have successfully shipped TFO and not had to roll back, which kind of demonstrates that this fallback algorithm is very effective. Question, John?
Clarification question, Jana Iyengar. What data do you send in these connections?
These are actually not, so these probes are using user traffic, so they're not active probes. So it's basically the Edge browser, for example, going to google.com. So, if you go to google.com twice, essentially those would, two of those connections will end up acting as the probes.
Oh, so I see. So when you say multiple connections, they're not multiple simultaneous connections.
No. So
they're,
yes,
you're choosing some connections arbitrarily, perhaps.
Yes.
But
it's basically one connection ordered by time. So essentially, it's like a semaphore. So only one connection is acting as a probe at a time. And the advantage of doing that is that if there's a real problem, we don't sacrifice too many active browser sessions for being able to determine that TFO works.
Cool. Thank you.
Stuart Cheshire from Apple. Your third bullet from the bottom, you talk about if a network hits fallback. So when you say a network, is that the local link, like the Starbucks hotspot is one network and my home Wi-Fi is another network?
Yeah, so we have a network identification scheme in Windows. So for example, you could use the default gateway's MAC address. There is a way to determine that the network is unique. So even if the interface is the same, when you connect to a new network, we are able to identify that it is a new network.
Okay, that's what I thought. So what happens if there is a particular website that I access, which is behind some kind of simple-minded defective firewall that breaks all TFO? So that gives the appearance that TFO is broken for me on 100% of the networks I visit, but only for that one site that's got the defective intrusion detection system in front of it.
That is correct. So in that case, yeah, the assumption here is that the problem is closer to the user rather than closer to the server. And the goal here was not to be increase coverage of TFO, but was rather to unblock deployment, which is, this is the first time we are able to, do it without having to roll back. So be as conservative as possible and start out small and kind of improve coverage over time.
Do you have more slides?
Yeah.
Go ahead.
Next slide, please. This is some preliminary data. Again, because this algorithm is extremely conservative, at this point, we find that around 26% of devices successfully use TFO and do not fall back. One of the problems that we have with the current algorithm is that if you noticed, a SYN timeout actually results in fallback, which could be due to bad connectivity. So because we don't persist success, it's possible that over time, the number of devices actually reduces, because now you could have a device that succeeded on TFO, reboots, and then next time hits a SYN timeout for bad network conditions and actually turns off TFO. So this is the preliminary number. It's possible that over time this number may change for the worse. We did an A/B test as well, targeting a retail population with TFO on and off. One of the success criteria for us was that there should be no measurable increase in page navigation failures, and that turned out to be true, which means the algorithm is actually working as designed. The failures that we are finding are correlated with geography. So we certainly find that there are certain countries where TFO success rates are very poor. We also find that they're correlated with specific networks. So there are certain networks where, TFO. Again, the data here is, I cannot present here, but if you have any more questions about that, I'd be happy to answer offline. Yeah, as I said, the SYN timeout heuristic right now makes this algorithm extremely aggressive in terms of falling back. So one of the future improvements we're looking at is only fallback if, on the subsequent SYN retry, we essentially remove the option. So fallback only if the subsequent SYN actually succeeds, which would be the case where it's not really a network connectivity problem. I wish we had made this improvement in the current release, but we'll have to wait about 6 months to get this data. The other thing we are looking at is, removing some of these criteria and see what happens in like an A/B test. And of course, we would also want to work with all of the networks where we're finding these problems to kind of improve the success rates over time. Next slide, please. So this is a basically breakdown of kind of failures that we're seeing. The black one doesn't show up really, but it's actually a reset in response to SYN. So if you notice, the SYN timeout is the bulk of the thing here, and that's likely because of networks that are, poor connectivity. So one point I missed earlier in the slide was that we only do this probing on networks that are determined to be connected to the internet. So that is done by an active probe, and which determines that a network is internet connected. So SYN timeout after that means that the network is actually, has choppy connectivity. It's not like we are doing this without determining first that the network is actually connected to the internet. Do you have a question on TFO?
Sure. So on one of your previous slides, Pat McManus with Firefox, and the one before this. There you go. We talked about full data timeout. I'm curious if you can talk a little bit more about what that is and the role it plays. So we've spent a bunch of effort trying to enable this feature, and the good news is we actually see, I think, a somewhat higher number than you report on the next slide of people who successfully use it, and it has a good impact. And we have a lot of mitigation strategies too. to the point where we're currently deployed, they reside mostly in the things you're talking about here, you know, resets, SINs timing out, no data being exchanged, so on and so forth. The one case that's killing us, though, is the combination of TFO successfully negotiated and TLS 1.3 seems to have a very high error rate in some environments. And that error rate is unfortunately not in any of these handshake scenarios. Like application data records flow for actually like several seconds, and then just like no data. It's infuriating. Suggestions you have about what you can do about that, other than, you know, a timeout strategy, which has tons and tons of false negatives, right?
Yeah, so I can explain. The full data timeout is basically not the SYN timeout. So essentially, you send data and then you hit retransmission timeouts and you could not recover. So you basically, essentially the middle box black hole the connection completely. So that would be the full data timeout case. Your point about TLS 1.3, we don't have experience because we haven't actually turned TLS 1.3 on in any of these experiments. So right now, our experimentation is limited to TFO, and we're not experimenting with either TLS 1.3 or ECN. So yeah, I don't have a good answer to that.
Where did full data timeout show up in your percentage graph of your rate of errors?
Can you please go to the next slide? One more. Actually, it turns out that the timeout is that case. So it's after the SYN timeout. So there are a lot of cases where we are, again, this could be due to bad network conditions. It might not really be due to TFO.
Jana Iyengar. So how does this? So first, thank you for doing this. And bringing the data here. This is absolutely very, very useful. Continuing along the thread that Patrick just started here, I think it would be useful to have some baseline numbers. You're obviously doing A/B comparison, but the number of timeouts is part of the total failures. But it's not clear how much of this is due to network error that would affect other connections as well. So normalizing this by that and showing if the error rates go up might be a good way of looking and seeing if TFO is inordinately being hit by this. I think there's a different kind of error also that I heard from, I believe it was Apple, that encountered some other errors also that are similar that would have caused it to look like a full data timeout after the handshake was completed.
Yeah.
So I think the full data timeout after a handshake is complete is actually a particular pathology that we may want to look at more carefully.
Sure. Yeah. Good feedback. We'll work on getting those numbers. Can you go to the next slide? Yeah, I'll rush through them. So quickly, an update on Cubic. So we did find that compound TCP is actually very sensitive to delay fluctuations. We find that especially in data centers with virtual networking that there's a bimodal latency distribution to which compound TCP reacts very badly. So we are switching to Cubic default. That's already shipped in both the client operating system for all connections and for the server operating system on high latency connections. Next slide, please. Next slide. Just a marginal improvement for client upload connections. Not really much to say here because most of the client connections are not really like high BDP, large congestion window connections. Next slide. This just demonstrates one of the problems for CTCP. We hit losses going from one region to other. It's a high latency link with a lot of losses, and CTCP sometimes gets into the state where it doesn't ramp up because it finds that the latency has increased a lot. Next slide. Cubic, on the other hand, is able to successfully ramp up regardless of variations in essentially end-to-end latency. So this just demonstrates that Cubic is kind of working better for our server scenarios overall performance-wise. Next slide. Any other questions?
Stuart Cheshire, Apple. Just wanted to echo what Jana said. Thank you for doing this. I take the point you made earlier that at this stage it's not important to use TFO in every place that it's possible. It's important to be able to use it safely and not have the customers worry about that. And if we can get 90%, then that clears the cobwebs from the internet, and then we can fight for the next 10% by fixing those broken middle boxes. So I think this is a great direction. Thank you.
Yeah, thank you.
Rabin? Thank you so much for attending the session. Okay, see you in London.